to this astrobiology seminar. Many of you were already at this morning's astronomy seminar and know Dane from before, but for the newcomers, this is Dr. Dane Greaves from the University of St. Andrews. Jenny is originally from London, where she also did her PhD at the University of London. She then continued to work within sub-millimeter observational astronomy at the JCMT and the UK Astronomy Technology Centre in Edinburgh. She is a reader in astrobiology at the University of St. Andrews and also coordinator of the Scottish Universities Physics Alliance Astrobiology Initiative.
Thank you. Thank you all very much for inviting me to speak today. As Andre said, I'm an observational astronomer, and I'll try not to use too much astronomer jargon because I realise people come from many fields in this audience. Please feel free to interrupt if something I'm saying you don't understand what I'm talking about. I'm happy to try and explain better. Okay, so this is work done not just by me but by several people within the Scottish Universities Physics Alliance, which is in a scheme within the last 2 or 3 years to link the physics departments in Scotland to make in effect one bigger and more effective research group. And the astrophysicists within those departments decided that astrobiology was something we were all interested in, and so we hired several new people, including myself, and have done what I think is some really exciting research, which I'll describe today, along with a few other things we've been doing. So this was built on work that was already ongoing in planet detection using both the transit method, where a planet passes in front of the host star, so we see a dimming of the host star, and also the microlensing method, where a foreground star lenses the light of a background star as it travels to you. If there is a planet around the foreground star, it acts as a second little gravitational lens and produces a blip in the light. So these methods can in effect detect quite low mass planets, but not exactly ones like the Earth. They tend to detect hotter ones orbiting near the star and colder ones orbiting further away. So we're not quite in the extrasolar Earth space yet, but these are very exciting results leading us there. So just to illustrate this, these are the WASP cameras. WASP is the wide-angle search for planets. And it doesn't actually require a conventional telescope. It requires to study a lot of stars and a large area of the sky and look for periodic dimming. So it turned out the most effective way was actually to buy conventional camera lenses. These are just Canon 400mm lenses, the last few of which had to be bought on eBay because they ran out at the supplier. And there are 8 of these cameras monitoring several degrees of the sky. And this experiment is now running very successfully, so you can see some of the WASP detections here. They're just sketched to show you the relative size of the planet and the host stars. So I think they're now up to 18 detections, which is very, very successful in the field.
Where is flowing?
Where is what, sorry?
Yes. No, the camera.
One of these is in the Canaries and the other one is in South Africa. So. And the other part of the experiment, the microlensing, requires telescopes, somewhat larger telescopes, scattered all around the world. So these are some of the ones illustrated here in the robotic telescope network. So this microlensing takes longer. As you can see, the rising light curve is due to the lensing of the star, and it lasts for several weeks. And the small blip, which is actually the planet detection here, lasts for a day or 2 days or something. So you require telescopes around the world so you can continually monitor it. So one of the telescopes sees the star above the horizon at night. This is not what I myself am directly involved with, but it's led by Andrew Cameron and Keith Horn in St. Andrews and was the basis of our astrobiology program. And as I say, the new WASP experiment, Super WASP, I think now has 18 planets. This is just illustrating, so the red and blue ones are the WASP ones. This is now a few months old, and some detections from other people. And this is actually just a plot of the size of the planet, which you can measure by the area of the starlight it's blocking out against the measured mass of the planet. And this plot is really just showing these planets all have different densities, so there's a wide diversity of planet properties within this sample. So we can fill in not just planets like Jupiter and Saturn, but much denser planets and much lighter planets. And RoboNet was involved in what until very recently the most low-mass planet ever discovered, which is about 5 Earth masses. So we really are narrowing in on the regime of rocky planets and planets that could be like the Earth. Okay, so as I said, built on planet detection, but we wanted to do more broad-based astrobiology than that. And what we've done is to combine the strengths of individual people in astronomical observation, and also in theory, and even in lab-based and experiment. And a lot of this work is because of the new people we've brought in. So it's myself in St Andrews, and Dr. Ken Rice as a lecturer in Edinburgh, and 4 research fellows spread across our sites. So altogether we have astronomers in St Andrews and in the bigger cities of Glasgow and Edinburgh, and Strathclyde University, which is also in Glasgow. So we have at least 4 universities with astronomers, and some other related people in Scotland, such as geosciences researchers in the University of Aberdeen. Indeed. And we were also given some equipment funding, a lot of which went into a supercomputer to perform some of the simulations you'll see here, and a bit of which went into the experiments I'll show as well. And also we've set up a new, effectively, graduate school to teach people doing PhDs about all kinds of astronomy and physics, but we have a new Introduction to Astrobiology course, which has brought in the skills of many people, geologists, biologists, to talk about the possibilities for alien life, earliest life on Earth, and these kinds of things. And we teach this, because we're very scattered, we teach this over a video link to all the various classrooms, which can be a very strange experience, because occasionally my classroom is empty, but I'm looking at 4 or 5 other classrooms with students in across Scotland on a monitor, which is a strange teaching experience, but we've actually found it works quite well. And the reaction to the astrobiology course has been very positive. So I just want to show you what we see ourselves as doing within astrobiology, and we are mostly astronomers, so this may not be astrobiology as you see it, but I've put up the names because people in the room may know some of these people. So broadly it goes from what is the raw material for planet formation, which I was talking more about this morning. So small rocky particles, dust and gas as a reservoir of material around young stars for planets. The actual physics of how stars themselves and planets form, observing the flattened disks of orbiting material around young stars where planets actually do form, detecting those planets, all kinds of planets, a zoo of very diverse planets, different densities, different orbits, different masses and sizes. Something I'm particularly interested in, which is trying to find systems where there may be habitable planets, where there may be planets with water, and risks to life of comet impacts on planets. And then, very generally, what are the life-supporting environments from astronomers and astrochemists in particular point of view, which I'll talk about at the end. That really has required a lot of us and a lot of imagination to think, what could we add? Okay, so I'm just going to talk about 3 examples: how you stick a planet together, how you take an image of that planet, and how you might look for life. And these are actually not 3 very closely related subjects, but they're things we did because of SUPER that we wouldn't necessarily have done otherwise, or we couldn't have done otherwise. Okay, so if you're starting to make a planet, the dust, small rocky particles you inherit from the interstellar medium when you form the star are less than a micron in size. So you obviously need to stick these together to make larger rocky bodies, so you can make rocks and then asteroids and then planets by merging these bodies. So you can study this either by theoretical, simulating the physics involved, or more directly by just trying to stick rocks together in the lab. It turns out it's very easy. You can show by experiment it's very easy to make small particles, so you can make these little aggregates. So if these are the less than a micron size pieces you start with, you can make an aggregate like that quite easily. Submicron sized particles stick together very well. But as you can imagine, if you collide 2 of these, you tend to break the arms and legs off. You don't make a bigger ball of dust very well. Now theory tells us that in the conditions in circumstellar disks, there'll be plenty of gas there, so it might be quite a viscous disk, and things could be moving quite slowly, and maybe they could merge quite slowly. But it's very hard to follow this in an accurate computer simulation. For one thing, we don't really know the exact shape these little aggregates are going to be. So this is something that it's easier to do by experiment. But because circumstellar conditions are very different from those in the lab, it actually becomes quite hard. You want to do it in conditions where effectively you have very little gravity, so the particles are almost in free fall, and you need conditions to be very cold, because that's like where planets formed in the solar system, so much colder than in your lab on the Earth. Okay. So this is the problem. Again, these fragile aggregates tend to shatter on impact. So some studies had already been done. There's some very good groups in Germany doing this. This actually, they bought a crossbow so they could fire things into other things. Gerhardt told me they weren't allowed to fire it on campus at first because they thought they would kill a student because it had a range of 500 meters and they thought people might be irresponsible. But anyway, they've done some nice physics with this, and they've taken some images of very small scale processes, and they found that you can fire a small body into a larger body and it will embed itself quite often. So you can build up bodies, but where does this larger body come from in the first place? Where is your first asteroid, for example? So this is something that's been led by Helen Fraser, who's my colleague in the University of Strathclyde in Glasgow, and she's been involved through the European Space Agency's student flight opportunity. So what they actually do is they do microgravity environments in a plane doing a parabolic flight, so effectively a small free fall segment in the Earth's atmosphere. And this has been very successful. It's something you can apply for as a student team, which is obviously very popular. And then you put together technical people and have the idea, and ESA give you money to carry this out. What's new about what Helen's taking part in is that these are the first experiments done with icy particles, so using cryogenic equipment, which is much more realistic of real circumstellar disks. And this is something that you can't do. A lot of the German experiments that gave very nice results have been done in drop towers, so you basically drop the experiment, but I don't think anyone will let you drop an expensive cryostat to do this. And this is something that we got involved with as well when Helen was a bit short of money, so Super allowed some of this to take place. So this is the plane they use, as it does a free fall arc, essentially. It does about 70 of these in one flight, hence the name Vomit Comet. And here they all are in one of the zero-G phases, and one of the experts on board, this is him sticking Helen to the ceiling during this flight. And there she is in free fall. It's pretty amazing when you see the movies of them in flight, because the arc actually only takes about 10 seconds. So you're told release, and you take your feet out from under the securing straps, you rush to your equipment, you set it going, you press the buttons or whatever. 10 seconds later you have to be back in position to strap down as the plane's power comes back on again. So it's all a bit lively. So I've got a couple of movies Helen made of the experiments as they took place in a flight last year. This is just some of the equipment. I showed this more when I gave a talk within Scotland to show what the money had paid for. But this is the particle container, and the particles are spat out, and there's a piston that powers the particles. So we're pretty much at the temperatures of icy regions like Jupiter's orbit, where planets might form, and we've got reasonable sized particles and reasonable velocities. They're not impacting very fast because you require a very large space if you're going to fire them together very fast to track what happens. So that's a bit difficult in an aeroplane, but it's reasonably realistic and certainly better than what's been done before. Okay, so I hope the movie will run. Okay, that's the one with rocks. So small rocks collide with each other, and as you saw, they break up a bit and tumble away. This one should be the one with ice cubes. So not so much breaks off, and they go more into spin. So if I can maybe go back to that again. Okay, so that's the sort of crumbly ones, and that's the icy ones. This is the first time this has ever been done. So we haven't really got the full scientific analysis of these results yet, because it's quite recent. But what we're doing is colliding for the first time cold particles of equal size, rather than requiring there to be a large body already there. We're a bit disappointed that the ice cubes didn't really stick together. In fact, half of them still break up. But it certainly wasn't worse than with the warmer, just little rocks. The interesting thing is that the energy of the translation as they move across appears to go more into rotation. And if they're then spinning and two of them have counter spins, maybe when the next time, which we can't do in the experiment, but if they collided again in a real disk, that would kill some of the translation energy, and it might be good for them to stick together later. So it's very early days, but it's quite promising that we're getting more towards how you might be able to make planets. And this is very vital stuff, because the earlier experiments suggested that you could make something maybe a few millimeters in size, and you could never make anything bigger, which would be rather a small size for a planet, a bit inadequate. Okay, so we think this is the second part of the investigations we've been doing. So we think we might be on the way to figuring out how rocks stick together. So this might be something real stars do with their disks and make real planets. But we want to know where and when these planets form around real stars. So what kind of planets do you get? What kind of orbits are they on? How long does this take? So something we've been doing on the astronomical observations side is to use this very large telescope. Sorry, I should say Green Bank. It's a very rural part of West Virginia in the United States. It's the National Radio Quiet Zone, where they've recently built this 100-meter radio telescope, which is a very powerful thing. So what we've been looking for here is any signs that these centimeter-sized bodies that we think we might now be able to make an experiment, any signs that these really exist around real young stars. So what I did was to go out and do a survey of some real young stars in associations of young stars in the constellations of Taurus and Ophiuchus, and look to see if there is evidence that they have grown what is in effect, dust particle that size, a small pebble. Now, because a dust grain cannot emit a wavelength larger than itself very efficiently, so if you see a centimeter-sized wavelength from dust emission, that means there's centimeter-sized particles there, which is very handy. So what we did was this plot, I'm sorry this is a bit confusing, but this is going to longer wavelengths this way. These were some existing measurements of brightness at millimeter wavelengths, and then if you carried on along the black line, that would show you that there are technically black body particles there, so particles much larger than the wavelength. We don't quite see that, but we do see, if we continue the line, where we're getting some centimeter wavelength radiation from this dust, which is close to this black line. So that's very strong evidence that there is pebbles growing around these actual young stars, which are about 1 million years old, or in some cases a few million years old. But just measuring the total amount of radiation from rocks is kind of boring. It doesn't give you much information compared to what a picture would. So the next thing the team did was try and get an image of planet formation in action, which I already talked about a bit this morning, so apologies if I'm repeating myself to people who were around at this morning's talk. So what we would like to do is, if we can get very high angular resolution on the sky, is to look at one of these circumstellar disks where planets form and see what processes are involved. And to do this, we use the Very Large Array, which is in New Mexico in the United States. This is it spread across the plane. This is actually in its most compact configuration, so we used it when there were telescopes. They move them around on lorries or something, when they were spread all over the place. And also there's an extra one they use, which is up in the mountains somewhere, which is 50 kilometers away from the main array. So what this gives you is a very large interferometer, and therefore it's working in effect as a telescope up to 50 kilometers across, so you can get very high angular resolution, very large detail. And we realized that in this particular arrangement of the telescopes, it was the first chance it ever been to take an image of a circumstellar disk where we could resolve things as small as the size of Jupiter's orbit. So obviously it's not very small, but it's the first time we could actually take a picture that's anything like on the scales of real planet formation. And it turned out this is very, very difficult, so we picked the brightest disk that was in the constellation of Taurus and just tried to take a picture of that. So this is the image we got. It's terrible. It looks like somebody stood on a frog or something, but it's completely squashed. Anyway, what we're looking for really is something like this. And this was a previous image given this shape to the circumstellar disk. So it's a disk of dust, and it's slightly inclined at an angle, so it looks like an ellipse. What we did manage to image was the inner parts of this for the first time, These are just pictures showing it in slightly different ways, so it's probably easiest to look at the main one. And this is the inner parts of this ellipse. And this is about the scale of Neptune's orbit. So what we're detecting here is large dust grains available to form planets, certainly on the size scale of the outer parts of the solar system. There's some bright stuff in the middle, we're not quite sure what's going on, and the white arrow shows something completely different, in fact. Emission coming out in these directions is to do with, this is a very young star, it actually has jets where it's spewing some stuff out into space. So that's why the whole thing looks very confusing. But then when we looked at this more carefully, we realised that there's this feature up here as well, which is a real feature and is associated with the star as far as we can tell. But it's a very long way out from the star. Okay, so we looked at this and we realised this again is, I'm sorry, this is a bit technical, this is showing the flux versus wavelength again, and a steep spectrum like this means that this is dust emission, whereas a flat spectrum would mean it's some other kind of emission. Okay, so this is for the disk as a whole, which confirms that very large dust particles are there. We detect them up to a few centimetres, and we infer that they're up to 10 centimetres across, so you've got like fist-size dust grain now, which is pretty impressive. And it turns out from two measurements that the spectrum of the little compact object in the upper right of the disk is very similar, which means that's also made of very large dust grains and presumably also some gas mixed in with that. So if we make some standard assumptions for how you convert the brightness of the dust emission to a total mass, we get that this is a thing in orbit of about, actually now we think about 10 to 14 times Jupiter's mass. So it's not any kind of protostar, it's actually a protoplanet, which is the first time anyone had imaged anything like this within its disk, and a thing so very young, because this star itself is a very young star, less than 100,000 years old.
So you mean it's an assembly of centimeter-sized particles that's moving together?
Yeah. So what we think is happening is this actually agrees with one of the models for how planets could form, and it's been a very controversial model. But the idea is that you have, if you have a disk of material orbiting around the star, and the disk is relatively massive, in this case about half of the star's mass, you've got a situation which is very unstable for gravity. You've got huge mass orbiting the star, and then sections of the disk that were initially slightly lumpy could in effect have their own gravity and just collapse out. So this is where we think you can make a protoplanet just by spontaneous gravitational collapse, and then it cools, it releases energy through radiation, and becomes a proper planet very much later on. But because this whole thing happens effectively in a few orbits of the star, a planet on this very large orbit could effectively form in only a few hundred years, which is pretty surprising. But this does actually seem to work. So Ken Rice, my colleague in Edinburgh, stepped in at this point and said he could do a simulation of it. And in fact, I've got a movie of that in a moment. He managed to make an object in his simulation using what we observed for the mass of the disk and the mass of the star. So he didn't cheat or anything, he just set it up with the physics as realistic as possible. And he made something that was almost identical in the simulation to the real object. So we really do think we're seeing a protoplanet forming. Okay, so this is the movie. It made seem too much Star Wars. I'm sorry about the graphics, but okay. So the disk is unstable, which means it develops these trailing spiral arms, and then a region which has a bit more mass becomes the protoplanet.
And what are the initial conditions for such a calculation? Like what kind of dust distribution and what kind of density do you need?
Sorry, he's gone a bit Star Wars again here. He just uses test particles, which I think are meant to be sort of boulders of rock, and then he just sets them up initially in a smooth disk of about the size and mass we observed, and just lets it run. You have to ask him for the technical details.
So it's really aggregating from the boulder size up?
No, the physics of grain growth is not included in it. It's kind of assumed that the particles are present, and because the simulation is only running for 1,000 years or something, you know, you wouldn't expect particles to change much within that time.
Do you know anything about the particle dispersion velocity or the temperature of the dust?
No, not yet.
And how about the observations? I mean, that's of course the main problem why this may not work. if the
Yeah,
temperature is too high?
I mean, Ken has also run some later simulations which did not fragment. We are as realistic as possible, and the disk and star masses are, where it does, are slightly higher than the preferred ones from the observations, but well within the bounds. The temperature, we just assume the material is in thermal equilibrium with the star, which has a known luminosity. So it's as good as we can get it from basically what is an image at one wavelength. And there are no observations of the gas, or at least not on this high resolution. So it's very much, at the moment, there's very little extra information that we could add in. But we know with our best guesses for the physical conditions, it does actually work. So,
Could I just add, I mean, but observationally it must be extremely rare if it only takes like 100 years to do it.
yes, I think it is exceptional. So there are hundreds of stars in the Taurus Association with disks of various masses, and we picked the brightest one, which is the ideal situation for this to work. When we're in that ideal situation, it does work. We wouldn't expect it to work in hundreds of other disks. There's also, interestingly, this particular star, HL Tau, is unusual in Taurus, that there's another star somewhat to the left, because the stars in Taurus are very sparse, they're very scattered. So we thought it's a bit unusual to find another star roughly in the same part of the sky. And then we looked up the motions of the stars across the sky, and it turns out this one's going this way, and the companion one is going that way, which means they would have passed each other, at least projected in the 2 dimensions we can measure. They would have passed each other about 2,000 years ago. And it is possible, well, this is a very unusual situation, but we just happen to be observing an unusual situation. It's possible that the flyby of this other star gave us a great gravitational tug to one side of the disk and made it very unstable. So we're not saying that this is anything like a usual method of planet formation. It's just the pieces of the jigsaw come together very well in this particular case. Okay, so I just wanted to say that this is pretty exciting. We're going to try and do some more observations, and indeed we may be able to look much closer in. So we've proposed to use the Merlin network, which is the multi-element radio-linked interferometer network of telescopes in the UK. As you can see from the picture, they go across most of England, so this has a very high angular resolution, and for HL Tau would enable us to image within this area here, so inside Jupiter's orbit, and at short wavelengths, actually at the scale of the Earth's orbit. So if we managed to find 1 or 2 very bright targets, we could look right in here and see if there are big lumps of dust that might be a sign of extrasolar Earths forming. So hopefully there'll be time for that. So the last of the 3 topics I wanted to talk about is, well, we're interested generally in how often stars might have Earth-like planets. But as we've seen already from the transit and microlensing data, there are also hot Earths and very cold Earths. So we need to think a bit more generally about what might be habitable environments. So there are missions that are looking for things that would be a lot like the Earth. So in the future, something like ESA's Darwin will hopefully try and find, by direct imaging, extrasolar Earths, and then by spectroscopy try and look for something like the spectrum of the Earth's atmosphere, which is very characteristic of life. Things like ozone traces oxygen, and there wouldn't be oxygen in our atmosphere in large quantities without life on Earth. So this is very, very difficult technically, and it's a long way off, but it's an interesting thing to do, to think about what might be livable environments. So how you get livable ingredients like an atmosphere to a planet, how the people on that planet survive if there's comet impacts and that kind of thing. So that's my kind of area. I was really hoping I could talk about this today, but unfortunately I haven't got the data yet. So what we've done, which I'll be able to talk about another time, is try and reproduce the deep impact experiment. So this sent a probe within the solar system to crash into a comet, and took a spectrum of the gases and crystals coming out and detected water. What we realized we could do is there's an extrasolar system, one particular star, where we detect the spectral signature of dusty debris, and it's been modeled as the breakup, presumably under a collision, of a single supermassive asteroid. So we got time with the Spitzer satellite to take a spectrum in this extrasolar system and see if there's also water there. So it would be a really exciting way of looking for water in another solar system that could end up being incorporated in a planet. And one very large asteroid containing water could have had a very big impact on the Earth for whether we had oceans, how deep our oceans were, the composition of the water, and so on. Unfortunately, I got the data. They were taken. The data were taken in the middle of August, and I haven't got them yet. So they're somewhere in the downlink from the satellite and coming through the data pipeline, I hope. But that's just generally to say this is something we'd like to be able to do in the future. But something we have been doing is looking for other environments that could host life within the solar system. So it's been suggested for a long time that icy moons of Jupiter and Saturn that have thick ice crusts, and of course we heard about this from the talk yesterday by Ingvar, right? That there is ocean water under these thick ice crusts. And it's been suggested that life could evolve here independently in these pockets of water. It would be very difficult, but there are sources of energy. For example, if the deep cracks on the surface of the Enceladus moon went all the way down to the water layer, it's possible some sunlight could get down through those cracks. Probably more likely is this thermal energy from underneath. So the middle of the moon is molten because of the tidal effects that Amy talked about, which maintain a molten core within the moon. So that provides the heat source from underneath. And indeed, this is very analogous to places on the Earth that do have life. So this is a picture on the seabed of one of the so-called black smoker regions, which have very thriving ecosystems, often very differently based to life on the surface. So sulfur is used very heavily in these volcanic environments by some of these organisms. So the picture is actually a cloud of sulfur being released by microorganisms that take sulfur molecules and get energy out of them and release clouds of sulfur. So we wanted to get in on something really astrobiological, which coming from an astronomy viewpoint was a little bit difficult, but I think we've come up with something because we can observe the solar system. So we focused in on Enceladus, which is the moon of Saturn, which Amy mentioned has cracks where water is coming out from below, effectively in a geyser or however you pronounce it. So this is one of the discovery images. So this is the moon Enceladus, and it's embedded in one of Saturn's rings. And when they look closely, they notice there's a geyser plume coming out from the South Pole, which is pointing somewhat towards Saturn, which is not seen but is in the middle of the image. And then again, I mean, these are obviously the Cassini images, and Amy talked about it much better than I could, but they did some heat mapping and found the hot stripes, which are effectively the cracks in the ice, and they located particular parts of the gas plume with these stripes on the surface. So this is unique in the solar system in probing the subsurface conditions. And again, more NASA results from Cassini. They found a rich chemistry in this material coming out from below. So they found a lot of water. This is just the percentage of material coming out in the plume of various kinds. And the bars on the side represent the proportions of those elements that are found in solar system comets. So it's similar, reasonably primitive chemical material, but it's not exactly the same. But they found a lot of interesting molecules there, methane and so on, which could, and some organics, which could potentially be used by life or be a sign that life is using them. And if there are any unusual relative abundances, it could show something that's different from just your normal astrochemistry going on. So we realized that we could actually add some expertise for this. So Cassini is in orbit around Saturn, obviously gets a very good close-up view, can go and visit Enceladus. But we have very large telescopes on the ground working in the millimeter, and these are very well adapted to looking for transitions from quite large molecules. So quantized rotational transitions of molecules produce a millimeter wavelength emission at a very precise frequency associated with the spin rate of the molecules. So these are the telescopes we use. This is the 15-meter James Clerk Maxwell telescope in Hawaii, and this is the IRAM 30-meter telescope in the south of Spain. So these are the world's most powerful facilities. We tried first at JCMT, and in fact they had a new camera for taking spectra with installed, and they opened it up to common use on the 1st of March and gave it to us. And then realised we were the first users, and we had to do the most difficult possible experiment because the moon is moving around Saturn, and JCMT is not set up to follow moons. It can follow Saturn, but the moon relative to Saturn is moving in both position and velocity, and there was nothing in the software to allow us to do this. So we basically had to keep adjusting things by computer just to try and track the bloody thing. IRAM, it turned out, when we went there a year later, were able to track Enceladus, so we could sit back a bit more, but the real discovery data were with JCMT. So we wrote this telescope proposal for JCMT, which basically said, we don't know what to look for, but we'd like to find aliens, please. They rejected it the first time round, so we wrote it with a little bit more guesswork in, and they said, oh, all right then, go and look for some molecules coming out in this geyser plume. And because we didn't know what would be signs of anything interesting, we just looked for lots of molecules. So at first it was very disappointing, and we didn't detect these molecules. And I was really hopeful for sulfur because of the analogy with the seabed. There would be some interesting ratios of sulfur-using organisms, and we'd see some sulfur molecule lines, and they'd have a very strange relative abundance, and we could say, aha, sulfur-using organisms. Because we didn't see any of them, we couldn't do that. But we did actually get a detection in the end of methanol. So this is the first detection of any molecule using a ground-based telescope from Enceladus, and I think it's the first detection of methanol. I don't think Cassini got methanol. So this looks really, really boring, but this little blip here of this particular velocity, this thing is actually the line. And that was quite hard to do, so we went to IRAM, which is a telescope 4 times larger in collecting area. Because we had this, they allowed us to observe for a bit longer, and we got this earlier this year, which is much more obvious, and is clearly seen above these squiggles, which are just the noise in the spectrum. So we were pretty excited about this. And indeed, just by looking simply at the data, there's some interesting and novel results. So to make the lines as bright as they are observed, we found that the plume of material has to be actually quite large, and that's about 4 times larger than the moon is itself. Whereas when you look at the pictures taken with Cassini, the plume is quite a small thing close to the surface, so somehow these molecules are getting much further out in space. It seems to be possibly varying in time. We didn't observe exactly the same lines at the 2 telescopes because they work at different frequencies, but they're similar lines, and it was brighter one year than the other. And the last thing is that what was actually measured along the x-axis in those spectra is the velocities, and we found out that the methanol appears to be moving very fast with respect to the moon, as though it's being ejected at very high velocities, whereas Cassini, I'm not sure exactly how they do this, but they infer that it's only coming out at just over the escape speed. So in fact quite a lot of the water in the plume is expected to settle back onto the surface of the moon. So this may be some very strange interaction on large scales with Saturn's magnetosphere, for example. Now we really are starting to guess, and I'm going back to JCMT in January to try and get another data point on this curve to see if this model works. But our toy model is if you were looking down on the Saturn system, so above, so that's Saturn, I know it's not purple, but anyway, that's Saturn, and this is Enceladus going round. It's trailing a plume of gases behind it. And we observed by coincidence at different parts of the orbit when we observed in 2007 and 2008. And all you actually measure in the spectra is the component of the velocity towards you. So if it was being trailed very rapidly behind the moon with the same velocity in the 2 cases, because of the different orientations, we would have seen very different velocities, and these are the velocities we saw. So this model does appear to work, but we're going to try and get a 3rd data point somewhere around and see if we can understand this very strange physics. So all of this was completely unexpected, and indeed the telescope people on the 3rd proposal were not very happy with us. We couldn't explain it, but you know, this is unexplored territory. There's no way we could explain it yet till we get more data.
What is the distance in oxygen between Saturn and Enceladus?
It's about 40 arc seconds of maximum elongation. So the telescope beam is actually quite a big thing. So this is not really drawn to scale. But we can say, particularly as we were using camera instruments, that we've got a beam pointed towards Enceladus and then other beams, different parts of the ring system in Saturn, so we can say this isn't a signal that's everywhere. Okay, so this is a very open-ended project, but we want to say, well, is this Is this methanol some kind of pristine subsurface molecule just being ejected? Does it even relate to maybe methane-using organisms? Could they be producing methanol somehow? Or is the stuff that Cassini didn't see close to the moon, is it actually being produced in space in the plume? Which would be an amazing astrochemical laboratory if that's true, because the crossing time of the plume is only a couple of minutes, so you'd have to have astrochemistry, you know, working like that. We also want to see, since this stuff seems to be moving very fast, if it's a way of kind of seeding the Saturn system with methanol, and we realise that we can actually look for heavier molecules with some of these other telescopes in the future. So I think that's about all I had to say. Yeah, that seems to be nearly the end. Except that our astrobiology initiative has been really exciting for those of us involved in it. We think we're part of this move towards finding the first one Earth mass planet, some suitable habitat for life. In particular, Planet Finder will be a successor to RoboNet to do microlensing and look for much lower mass planets and closer analogues to the Earth. We're getting very interested in this idea of how widespread water is in the universe, because we come from a background of observing water and astrochemistry. So we're associate members with the University of Hawaii in their bid for NASA Institute of Astrobiology status, which hopefully we should hear about reasonably soon. We've got some instrumentation work going on that I didn't have time to talk about, but one of our research fellows, Ettore Pedretti, is working with the people in Edinburgh on some instrumentation that could be a key part of Darwin, if that's eventually built, to look for extrasolar Earths. And we've just applied for, of course, a whole load more funding, hopefully to pay for some of this exciting equipment in particular. So that's basically it. The last thing I wanted to do was advertise to you that we have a workshop very soon called Habitability in Our Galaxy. So if you have a chance to come to Edinburgh, we would be very pleased to have you participate, present something, or just join in some nice discussions. So thank you very much. Yes.
Daniel Hesselman was here this week and gave a talk showing these zero gravity collisions. And one of the issues that came up is the collision speed. So there is a threshold velocity for small particles and for large particles. But for ice in particular, the velocity range that he studied would clearly give what you showed. You observed, but higher velocity collisions could actually give rise to sticking and lower temperature, because it's very hard in those experiments to go down to, say, 10K, where people observe using UHV systems something called amorphous solid water.
Yeah, it's difficult to get everything right at once, because you want the effectively vacuum conditions of material orbiting a star, very low densities, and you want low temperatures, and you want the high speeds, and that's not really compatible with any reasonable size of equipment space. But hopefully by synthesizing some of this and understanding how the physics works, we can do it much better than we could before. So particularly the speeds in the experiments I showed are a bit low, whereas on the other hand, some of the experiments with gas guns, where you use a gas-propelled system to fire things into a target, those are too high. But hopefully by interpolating between some of these results, we'll get to the parameter space we need.
So is there any facility in the UK associated with this initiative where you are going to do such experiments, or is it?
There's the light gas guy in Kent, which is in England, so it's not part of SUPER, but Mark Birchall, who runs that facility, we chat to him quite a lot. So yeah, we can do some joint things. And the kind of speeds they use are about, I think it's about 8 kilometers a second. They tend to smash things up more, but it clearly spans a much wider range, the very high end of the range of velocities compared to what we do. And it's not really certain how fast things collide in circumstellar disks as well, because they orbit fast, but two things that collide could be going on quite similar orbits, so they could have quite a low speed encounter.
A different question is you have this, I guess, evolving program there. Is that there's no one now in applied mathematics, or you said you were mostly astronomers, it seems that chemists and applied mathematicians might be interested in these things, everything from data mining methodologies. Not that astronomers haven't covered entirely all of those areas, but is there any, I mean, there's plenty of people in these fields in Scotland.
Yeah, I mean, the funding we can really only direct through physics departments, so we directed a bit for the equipment to Helen, although she's not formally within Super, and she's not a Super appointment, but she is, as it turns out, in a physics department in Glasgow, although she's actually an astrochemist. So, you know, we're certainly bringing in people with very different backgrounds, such as chemistry, and then, you know, Ken's background is pretty mathematical for doing the simulations. It's only a matter of where we can, like, visibly spend money that limits it to physics.
I have sort of related question to that. So within this super collaboration, super, you know, it's not such a good word in Swedish, but we can pick it up later.
We had a bit of trouble with the supercomputer, and then we realised it was a dual processor array, so they stopped me calling it the super duper supercomputer. But
well, super, you know, in Swedish is sort of heavy drinking.
Ah, that's even better. Now I'm telling you that. Please, can we adopt you?
In this collaboration, I get that you're mainly astronomers, really.
Yeah.
You have not tried to expand into biologists, geologists, and so on?
So far, only in the taught course, which has biologists and geologists. So we have an evolutionary biologist who talks about her experiments on very small habitats, like islands on the Earth, and how that affects the diversity of species. And she's, you know, done some thinking, a sort of theoretical study about how you could expand that to, could life ever have evolved early in the solar system on asteroids, which is a very small habitat with, you know, extreme conditions. So far it's mostly been people chatting about ideas. I think it takes quite a long time to get research projects going. So, you know, we might be able to do something like with a biologist to include some microbes on our, you know, grains that we collide in the microgravity conditions. To me it feels like things are going very fast, and it's difficult to sensibly incorporate multidiscipline things at a very high speed. But, you know, if we get our second lot of 5-year funding, I think we'd very much like to do that. We've only been doing this for about, well, I've been in post for 2 years, so yeah, you know, most of us are very open to doing much more wide-ranging things as soon as we can.
Did you say the dust spectrum was much steeper than the gas spectrum? And did I understand it correctly that it was actually falling towards longer wavelengths sharply?
Yeah, when I was showing the green bank data.
Yeah.
The dust spectrum, it should be a frequency squared spectrum for black body dust, so that's roughly what we have.
But then long wavelengths have very small, extremely small flux.
Yes, essentially, well, in part because you can pack the same mass from lots of millimetre-sized grains into 1 centimetre-sized grain, but then its emitting surface area will be much smaller. So
and
these are very, very small fluxes.
And the slope is independent of the particle size, or does that actually also?
No, the particle size affects it. So if the particles are small, the spectrum is very steep.
Right.
It can be
okay, so then with age you would expect that the spectrum becomes shallower.
As the grains grow, it should become shallower, yeah. But this is not entirely clear from the data at the moment, because it's difficult to observe. You know, if we could find a star 1,000 years old, then we could observe. But you know, the number of very, very young stars is going to be very, very small. In the project we've proposed to look with a very high angular resolution, we've included objects as young as class 0 protostars, which could be as young as about 10,000 years. So hopefully, going from 10,000 years up to, I think the oldest is about 10 million years, will give us some sort of clue as to how long this takes.
And this tau, was that class 0 star?
It's class 1 actually,
class
so
1.
it's an older.
But it still does not have a jet yet, you think?
It did have a jet, yeah,
but a very tiny one. Or?
Well, actually it's quite, I don't know if it's been tracked out to very large scales.
You see it in optical then, yeah? Or?
I'm not an expert on this.
Because in this picture you showed there wasn't anything except for the arrow.
Yeah, it's because we're only sensitive to the very small scales. It's
Right.
been done with radio imaging extending a few arc seconds from the star, which is a much larger scale than we were looking at there. I'm not actually sure if it has large optical jets. We'd have to look that up.
Okay. Ah.
Yeah.
I just wanted to make a small announcement since we have got international guests here. There will be a summer school in Iceland with the theme of water, ice, and the origin of life in the universe, which will consist of a lectured part where topics from the formation and chemical processes of water in the universe to extremophiles and glaciers and hot springs will be covered. Then there will be an excursion part where we will visit glaciers, Mars-like landscapes, and also hot spring areas, which we will then also take samples from and analyze in a third part, in a laboratory part. The summer school will be next June, July for 14 days. There will be student bursaries for US and Nordic students, and also some limited amount of money available for European and other students from other nationalities. There is of course a website, and I would like to ask all international guests to hang up maybe one or two of these posters at their home institutions to announce this event.
That would be
Thank you.
great.
It's only open to students.
The main team A group is graduate students, postdocs, and undergraduates. Sorry.